well, let me briefly introduce for our colleagues. Yeah.
Okay.
So our today's speaker is Yongyao Chen, professor, director of the Institute of Marine Information and Systems. Nowadays, we've got different directions of work with him, and today he will talk for us about metamaterials-based acoustic warning system towards practical application. So, Yao, you are welcome, please.
Okay, it's my great pleasure to meet our friends in ITMO. And then today my topic is metamaterial-based acoustic warning systems towards practical applications. So this is our collaborative work with Maria and Angeli. So first is about the research background and significance. So we know that the acoustic warning system is actually be applied for various practical applications. For example, live detection. Usually, because in some programs they use helicopter to equipped with acoustic sensors, array sensors, which is they fly to some hard to reach regions to detect some call, help, and even some the breath of the person. So that they depends on a very sensitive sensors. So that is for live detection. And the civil security, because you know that in especially in US, they have some gunshot problem, especially for campers. So the campers, so the police, especially in California, they already launched some program. You can see that there is a acoustic array sensors here, which is located with a camera. So usually why they don't directly use camera, because camera sometimes, because they are full view camera, so their detection range sometimes is limited. So usually people now they are trying to use the combination of acoustic sensors combined with a camera to do a very good civil security. So first they will hear something, you know that. So you just imagine that the human being. So if you want to detect some dangers happen, usually always you will hear some abnormal voice first. Then you will turn your head to some specific directions, and you will find some dangerous events. So they use the same technique. They use an acoustic array sensor combined with a camera to do this kind of civil security detection. And also because of the drone issue, drone is actually, people realize that this is a kind of a very low cost but very dangerous equipments. So they also want to use acoustic sensors to mitigate the dangers of the drone. So why they use acoustic? So because you know that maybe we use radar, with a radar to detect some drones and to detect some targets. However, because of the cloaking technique, some drones they already have some cloakings, which is they can absorb the radar's wave in a very broadband spectrum. And also for infrared detection is another way to detect the drone and detect some dark targets. However, for some bad weathers, there is a challenge for the infrared detection. And also, of course, for cameras, they are good in indoor, but outdoors they always make some problems for outdoor. For example, they have smoke, and they have a lot of smoke and dust in this kind of a very battlefield environments. Then the camera they cannot work. So to mitigate the drawbacks of various detection techniques, so the acoustic detection warning systems currently is very promising field, which can be they can combine with other detection methods like radar, like camera, like infrared. So and even like laser radar. So this actually acoustic warning system has become a very important field in the warning detection systems. So this is another example. Sorry. Okay, so this is another example about using acoustic warning system for defense. So the first picture is actually U.S. Army. They have this kind of acoustic array sensor array systems in Iraq, because Iraq they always have snipers. Snipers, the U.S. soldier at the beginning they're always been troubled by the snipers, and then the snipers killed a lot of U.S. soldiers. So in order to detect where the sniper's bullets come from, they actually have this kind of acoustic antenna. Is a kind of array system in different very important locations, and also they put this kind of acoustic array system in their vehicles. And also this kind of device has demonstrated a very good potential to protect the soldiers alive. And of course, they can also be used for the some cannon and also some abnormal noise in the battlefield. And currently, people, U.S. Army, they try to miniaturize this kind of acoustic warning systems. You can see this kind of this is the shoulder, right? This soldier is actually put a shoulder. They have an acoustic array sensor on their shoulder, and then they have this kind of a device which can protect the soldier's life, and then they can easily to determine where the bullets come from, and then they can also recognize whether it's their enemy or whether it's their partner. So this is a very powerful system for homeland securities, especially for single soldier equipments. However, during the developments of this kind of sensors, they found there's a lot of practical issues, which is sometimes prevent this kind of acoustic sensor systems being used in outdoor and harsh environments, because we know that most of these acoustic warning systems will work in outdoor and harsh environments. So you can see that, for example, we usually use this kind of like a traditional microphone, and then we have MEMS microphone. So, but we cannot directly use them in the outdoor. Usually, we need to have a windshield. The windshield is covered on the the microphone, and then they have different types of windshield. One is the foam. So the foam is because they have a porous structures which can actually dampen the flow of the air, and then they can mitigate the wind noise. And then the other way, they have this kind of like a fluffy, windshield device, which is this one is actually especially used for very strong wind environments. And also, in order to protect this kind of microphone, they have this kind of windshield, and then they plus outer shell, which can protect the microphone being to the anti-collision. So what's the problem of the current windshield? Because most of the foam and of this kind of fluffy windshield, they are not waterproof. So if for example, the outdoor, the people hold this kind of sensor, they always go to the water, they have a raining weather, and then the foam will fill all of the water, and then the sun cannot go into the porous structure. Then it probably can do the windshield, but at the same time, the acoustic signals has been decayed very, very significantly. So in order to try to mitigate the rainy weather issue, people developed some waterproof microphones. However, the waterproof microphone also have some problem, because when you know that if you use some solid plates, which is to isolate water, your sensitivity actually will be decreased. So people currently, in order to have some waterproof, high sensitivity membrane microphone, actually they use a membrane structure. The membrane is actually the sound is actually to drive the membrane, and then they have a capacity change. But this microphone head is totally waterproof. However, you use the membrane. So in this case, the membrane is very fragile. So we know that in some applications, they are in some collision environments. There's a lot of collisions happen. So to avoid collision, and the microphones is actually they have a very solid the solid structures, which is a cover this microphone, and also they have this kind of a steel net to protect the microphone. But the same issue is, it seems that these microphones these shells is actually don't have the function to improve the signal. Sometimes it will decay some signals. So our idea is, because we know that our idea is actually like this. So we put the acoustic array sensors, and then is make a sensor arrays to put on the CT pole, and then this arrays the individual elements is actually coiled material, which is where people well-known structures. However, people don't realize that this kind of structure have a very promising and useful applications for wind suppression, and also as well as the acoustic signal enhancement. So this kind of sensor, because there are several advantages and important properties of this acoustic metamaterial combined with MEM sensors or a conventional microphone. So the first one, the microphone is actually inserted into the hole of this shell, and so this shell is actually can somehow improve acoustic signal for the enhancement, because they have resonance. It is like a low frequency resonator. And in the meantime, sorry, sorry, I get a cold. Okay. So in the meantime, because this one is also an artificial porous material. Can you hear me?
Yes, we can.
Yes, we can hear you.
Okay. So these coiled structures is actually an artificial porous structures which can mitigate the wind noise, and also at the same time it's kind of hard shell, so it has several important properties and advantages. One is it's windproof, and it is damage detection, because the function is like this kind of sensors. However, it has capability to improve the acoustic signal. So, and also because we avoid using the conventional foam and the fluffy this kind of materials, so it can also do somehow. It is maybe not. It can be waterproof, because we have some like IP6, which is a waterproof microphones, which can insert into this one. So it can actually have the waterproof and the damage protection. So because of all these advantages, we are thinking about whether we can use this kind of shell to improve the acoustic detection capabilities. So but before we do our research, we need to do some literature research, because we know that some state-of-the-art acoustic material sensors, they use various structures. For example, anisotropic wedge structures. They use kind of this whole array structure, this kind of like acoustic lens, resonators. All these sensors is actually, they only demonstrate their acoustic signal enhancement capability. However, this device, they are all in the experiments. They never tested the potential capability of a metamaterial in the outdoor. So that means our work, maybe, I'm not sure whether we can say it's first work, but anyway, it's our will that we can push forward for the acoustic sensor for the outdoor application, for some real applications. So this one maybe can resolve some people's they doubt about the practical application of acoustic materials, because they think that acoustic materials is hyper and don't have many practical applications. However, this work we really demonstrate it can work in outdoor, which is very important, which is very good results. Okay.
Sorry, Yongyao. Could we ask questions during your talk?
Mm-hmm.
Yeah?
Yeah.
Mikhail has a hand. Misha.
Yeah. Yongyao, I have a very question. Maybe I can ask you. I asked it already. already here. Just when you suggest using this meta structure and resonator, this immediately like gives you a narrow bandwidth in which it will operate. So it's immediately will make it. So probably it will limit somehow the applications because now you're only on a work in a specified band.
This is a very good question. So actually, we are doing some work with a cascaded cavities. You can see that. So this is the cascaded sensors. So
you want to extend the band. Right?
Yes, something like this. So you have several sensors. Then this is very similar with cochlear, because you know that the cochlear there, each sensor location is narrowband. However, if you have a band filter array, then you combine these signals, then it can be very good to get a broadband signals. So this will be not an issue for the resonance type acoustic resonators for future broadband applications. But we need to somehow to make a little bit complex electronic systems. However, because we already have some low cost data acquisition system, should be a not problem for the practical application in future. So which means
okay, thank you.
Yeah. Okay. So for narrowband application, So for narrowband application, this is a good question. However, I think this we can in future we can push forward to make a broadband detection. For example, we can do the voice recognition by using these cascaded sensors, and then to work in the outfield. So we can have this plan. If you have interest, we can have this work together to push forward this for this practical use. Okay, so in terms of sensor, because people already know that there's a enhancement of the acoustic enhancement of this structure. However, in terms of sensor system design, we need to know some specific details of these kind of structures. For example, we need to know the acoustic field distribution inside and along this structure. So in the cross section, which is this figure B, so you can see that the maximum acoustic fields is actually in the center of this structure, and also we are three-dimensional. So we also need to know in the vertical direction what acoustic field will look like. Then we can put our sensor in the strongest location to get the best signals. So if this sensor is a deep subwave lens, you can see that this in the center is the strongest, and then in the vertical direction, it's almost uniform along the vertical directions. So this actually can give us a very convenience. You can, because you want to insert your sensor into this one. Sometimes there is some deviation of the locations. So in this case, they're very unsensitive to the location of the sensor. So which is an advantage for the sensor design. And then in terms of pressure field enhancement, because we say that why this kind of acoustic metamaterial sensor have advantage, because the first one, it improved acoustic signal. The second one, it suppressed the wind noise. So these two factors will make your signal to noise ratio of your sensor be very significant as compared with as I introduced the conventional systems. So although it is narrowband, so this is narrowband, but you can see that the application is about maybe the half maximum is about 8 times. But actually we have stronger application, but we usually we want to keep some bandwidth, so we do a compromise. So we make this kind of a enhancement. Half with bandwidth maximum is about 4 times improvements of the pressure signal. And because it is an acoustic sensor, which is should be omnidirectional, because you need to hear from all over the around. So we do the directivity test, and it sees that the sensors is actually omnidirectional within its working bandwidth. So with these properties, we can confirm that it can be good for a narrowband acoustic detection. So further, we investigate the wind, the influence of the wind, actually the airflow which is applied on this structure. So without this shell, you can see that if you have some airflow applied on this sensor, because this sensor is actually a membrane, so this membrane is very easily being disturbed by this kind of airflow, and then you will have a huge disturbance because of the air pressure. And also, however, if you put this kind of sensor, so this is MEMS sensor, if you put this sensor inside the structure, you can see that on the surface of this microphone, so the figure A2, you can see that the surface of this sensor, the flow is being greatly suppressed. So you can see that in the figure A3, you have a very obvious shadow regions for the airflow within the structures because of these coiled channels, and it can dissipate the wind. So we also, because our sensors is actually pressure sensor, all these kind of acoustic sensor, they depends on the pressure field of acoustic wave. So we need to know to compare the difference of the pressure field with and without this shell apply on the MEMS sensor. You can see that the figure B, the pressure sorry, let me see. Without metamaterial. Okay, so the blue, the red one is the without metamaterial shell, and then you can see that the pressure is actually very large, and then with using the metamaterials, the pressure applied on the sensor is being depressed. Then we do, I think this one should be ABC. This one should be C. Figure C, we use a fan to blow. So in order to test the flow noise, we use a fan to blow this kind of sensor for a single elements, which is the fan is actually close to the sensor. And then we can get the flow noise power spectrum by using simulations. You can see that. So in the below 1 kilohertz, the flow noise without metamaterial is about 10 dB higher than without metamaterials. And then you can see the significant depression of the flow noise by using metamaterial, which is the blue line, blue curve. So also we do experiments to test this phenomenon, and then we observe very similar phenomenon in our experiments. So there's one phenomenon that we need to be careful. After after 1 kilohertz, you can see there's a saturation of this kind of noise of the sensor, because this one we detect the electric signal of the sensor. So actually why this one they become saturate after 1 kilohertz, because that is this kind of regions is the noise flow of the sensor intrinsic itself. It is not wind noise, because the wind, it is wind noise, but wind noise is not large as the electronic noise of the sensor. So in this region, the noise of this sensor system is dominated by the electronic sensor of the systems. So for simulation, we also add, because in simulation we usually don't have this kind of phenomenon, but we artificially add this kind of background noise. Sorry, this background noise is from the sensor itself. So in the experiments, we do observe this kind of intrinsic noise of the sensors. Then they have a saturation effect here. So which is a very good explanation of our sensor systems. So in this way, we know that this shell can actually decrease the wind noise especially in the low frequency regions.
Yongyao, can I ask a question here? So how do you do this simulation? Am I right that this is noise? So
yeah, well, let me see.
Wind is the source of this noise, right? That's
Let me open some simulation. Let me see. Notification, flow noise. So they use console to do this kind of a flow noise simulation. So they use some like a cylinder arrays to drive, to drive this kind of this mouse cannot see that. Where's that? Okay, here they use this kind of flow. This is the source, the flow source,
right?
And they put some disturbance here, because if you directly use a flow, then you will have some turbulence. But you need to have some scatters here to make somehow have a relatively stable turbulence here, and apply onto the sensors. So then we can do these kind of simulations.
But then, how do you figure out the noise coming from this turbulence? So
because you have some you have this kind of time domain signal, because this simulation is actually time domain signal. So your sensor, you have your pressure field in the time domain, pressure field signal in time domain. So this is actually the time domain. Then you do the FFT. Then you can do the power density spectrum of this kind of flow noise. So this is a simulation. Yeah.
So you use kind of a turbulence module, then airflow with turbulence, and then detect air pressure, and then we construct the noise.
Right.
Okay.
Yes.
Okay.
Yes. Actually, for console, it is not as good as Fluent. So my colleague is actually he used let me see. He used a Fluent to do some more specific. Let's see. Let me see. This is the simulation of here. So this is the experimental results.
The special software, right?
Yeah. This is console. This is console. This is the Fluent. So Fluent it will be more consistent with the experiments, because the Fluent is specifically designed for flow field. Console is kind of like not that as accurate as Fluent, as my colleague told me.
Yeah, that's clear. Yeah, that might be so it's not that specific for this kind of problems. Okay, yeah. Thank you.
Okay. Okay, so so now we know the acoustic signal enhancement. Then the second important property is the flow noise suppression. Then we will exactly to demonstrate. It is clearly demonstrated that the signal to noise ratio in the windy environments is actually can be improved. So then we come up to build a sensor array system, because the array system is for target detection and localization. So we can know the direction of where the sound come from. So then we do the sound source localization, which is just to determine the direction of the source, the sound noise. And you can see that. So this X-ray, which is the signal to noise ratio, and then this one, the vertical axis, which is the azimuth, RMSE, which is the somehow like a statistic values. The higher this value, the better the let me see. The higher this value, the worse the detection accuracy. So you can see that with using metamaterial for 0 degree. So 0 degree is actually from here, figure B, which is from the right to the left, which is a 0 degree. So 0 degree, you can see that. So for the low signal to noise ratio, so this acoustic sensor is actually can extend the low signal to noise ratio to -10, and then it still can have an almost 0 RMS, which is a very high accuracy. So if you keeping to decrease your signal, and also so signal to noise ratio is also you can enhance add the noise. So if you keep decreasing the signal to noise ratio, then you can see that maybe this metamaterial in some very low signal to noise ratio still can be effective. However, if it is too low, then these two systems has no difference. Maybe after minus 15 dB for the SNR. So for the 45 degree, it has the same phenomenon. However, it can give us some hints that for the tilt instance, there may be some. This is more accurate for tilt instance for low signal to noise ratio, because CITES RMS is relatively lower than the 0 and the 180 degrees. So this one, for these two sides, they are the same, and 45 and 135 they are symmetry. So you can see the tendency of this kind of curve. So this curve is actually clearly demonstrate the good capability of our acoustic sensor arrays for the sound source direction detection. So now we also do some statistics. For example, this one, this blue curve is actually the metamaterial. And then this red dots is that without metamaterial. And then you can see that without metamaterial, your target's direction is scattered everywhere. It's kind of random distribution, although it has some probabilities that it can detect the 0 degree direction. However, a lot of detection failed. They failed. However, for metamaterial, you can see that most of the detections, they are concentrated in the correct directions. And then we also detect some other directions, and then it really confirmed that for the source direction, it is very useful and for the detection. Okay, now then we know that for its detection capability, because of the signal to noise ratio improvements, then we know that we will test the outdoor. It is so this experiment is actually indoor. These two experiments, they are all indoor, because we use the artificial noise broadcast from the speaker to mimic the noise. However, then this is all indoor. Then we go to the outdoor. You can see that we have this kind of array system, and then we test two scenarios. The first one is the gunshots, and for gunshots, you can see the figure B. So we have this kind of road, and then we have different detection point location, which is extended to 1 kilometer. Now for the directivity, for the direction detection, we can see that without metamaterial, for these gunshots, you can see that it also have a very poor detection accuracy for the directions. However, for metamaterial, it has relatively high probability to detect its direction. So it extends to 1 kilometer. So this axis is the distance. And also for the voice detection, so we ask a girl to shout help. She just shout help, and then with and without metamaterial, you can see that it can go up to 100 meter with the ghost shots, and then it demonstrates that it can be used for various applications. And also we use an airflow. We use a fan to blow these sensors to mimic the environmental flow noise. Because the issue is that our outdoor experiment is kind of random if you cannot control the weather. So we just find a good weather. The wind is very mild. Then we can use this kind of the fan to mimic the airflow. Okay, so then we can see that for the time domain, because this is 4 microphones, we have microphone 1 to 4. And without metamaterial, you can see that the time domain is actually being distracted for the time domain signals. And with metamaterials, you can clearly see this is the gunshots. You can clearly see the pulse of the gun which is to show this 4 poles, then you can determine their delays to know the direction of the source. And also for the ghost shots, and then we can see that this is without material, their signal, their voice spectrum is signal regions spectrum is much lower than with metamaterials. And also, so this work is actually clearly demonstrate the potential of acoustic metamaterial for some practical applications. Okay, so the talk is relatively short, so there are some details. Maybe I also would like to discuss, for example, so what's the difference? So we actually analyze what's the difference between the coil-based metamaterials and our coil metamaterials model, because we use it's called multiple scattering, right? Multiple scattering, and then we found that currently most of the people they actually just treat this kind of structure as a continuous density, which is they have a uniform effective density outside the region whole. But however, we found that this model is not accurate if it is treated like a uniform density structure. So in terms of so this structure is actually a gradient density distribution, which can give more accurate results, because we can see this figure. So this one is actually to see that if you have the let me see. So this is the peak frequency, which is a deviation of the red star here. The green and red star is the accurate resonance frequency, and then this n is the layers, the number of layers of this effective shell. And then we can see that if we treat it like only one uniform shell, which is n equal to 1, and then you have a very relatively poor or not accurate estimation of his resonance frequency. However, if you have if you make this kind of like a gradient medium, then you can significantly improve its accuracy. So which demonstrate that this shell is actually can be treated as a gradient index, a gradient density structure. So this is the difference to understand the work of these sensors. And also, so in future, so this one is then we use this model, this kind of multiple theory based on the gradient density model. Then we can see that the experiments can fit the theory, the analytical model can fit very well with the experiments. However, there is some deviation here in the high frequency. However, in the low frequency, which is our working band, so this will be a very good model to predict its acoustic spectrum. And for the array detection, there's some equations to estimate the direction of the source. Then probably this one, well, don't talk too much about details for these equations. Okay, so basically this is our idea, and hope that we can make this work published. Okay, so is there any questions?
Mikhail, пожалуйста, please.
Yes, many thanks, Yongyao, for the interesting presentation. I was just wondering that so far you have a relatively narrow band structure. So when with one of the last slides, when you have shown great improvement in terms of frequencies, then clearly there was some maximum towards 1,500 kilohertz, which probably is good because like you can target your microphones for specific detection. But I was just wondering if we can think on some relatively easy implementation of multi-band frequency. I was thinking first option
I will show you this
along the axis, like if we can see the vertical positioning in the resonator, probably you can have some gradient of structural parameters so that it would have a best response to different frequency at different height inside.
Yes.
This is one point. And another point is probably if you use different sectors.
Right.
In that case, you can also have additional directional sensitivity, probably.
Oh, I see. So you suggest that we have different sections of this kind of
yes,
array,
yes. Like
right?
now they are all the same, pointing in all directions. They have all the same structure. But if there is some variation from sector to sector, then it can be translated into directional sensitivity with just a single element.
You mean it has a directional response by using single elements?
By using different structure in each sector of this. Like now you have 8 sectors which are all identical.
Okay, I see.
And probably we can use slightly different sectors.
Yeah, this is a good suggestion. Maybe in our next work we will try to use more sophisticated structures to mitigate this bandwidth issue. So currently we use a cascaded sensor device. So let me see here. This is the supplementary material. So this structure here. So we have cascaded sensor, and then we really see some relatively broadband response of these sensors. But we need to use maybe here there's 2 metamaterial shell. So and then we put 2 microphones here. Sorry, 10 microphones here, and then we can have relatively broadband, especially in low frequency, and then we can carefully design its spectrum to mitigate its bandwidth. Yeah.
All right, that's great. So that's similar to one of my things. Yeah, and regarding different sectors, yes, maybe we can also talk more about this, because I'm now in Qingdao, so
okay, great.
Can have a quick meeting sometime.
Yeah, sure.
With Andrei together.
Yeah, this is this is for the multiple resonators. We have a paper submit to APL materials, but this is for absorber, because we know. Okay. But for absorber, a good absorber, usually you can also improve the signal enhancement. Because a good absorber is also a good radiator, and then the pressure inside is also enhanced. So they are how to say that, they're reciprocal.
Yep.
Okay.
Okay, thank you.
Okay. So
could you please provide some details about your experimental measurements of acoustic fields indoor in anechoic chamber?
Let me see. We have here.
Yeah, here and maybe on previous slide, I think.
Here, yeah. So this is our facility. So you can see that. So this is the shell, and then this is the sensor without shell, and then we have a holder to fix this kind of metamaterial atom, and then there's 3 sensors which without have these shells. Then we play the same source, and then we can do the measurements, and then we have frequency scan, and also for rotation, because this one can also rotate the rotators they have. So, and this is our facilities. We have a DAQ amplifier and the sensor array. So this facility is not a complex. It's a relatively simple facility for the acoustic measurements. Okay.
Yes, thanks. Dear colleagues, anybody else? Any questions? Sergey, you're welcome.
Yes, thank you for the talk. So maybe I've missed that because my internet connection is not really good. But have you considered a kind of noise traffic? Noise related to the traffic, because when you do this outdoor measurements, so you place this device on the street, but you have all these kinds of different source of noises, and like how to distinguish between the like targets signal and the noise of the same let's say amplitude.
Yeah, this is a very good question, because we want to know for the traffic, our university is kind of a very far away place with the city. So we just find a night, a very quiet environments to do these experiments. Definitely, if you have traffic, there may be some we call it transient signals, because the traffic they are not. Sometimes you need to, for example, here, if you have traffic, then you will have the noise floor higher than this one. But that is another story. For traffic, we cannot mitigate the traffic, because if the traffic noise is overlap with the gunshots and the call and the human call, then this is an issue. So usually people will use we call it a blind source separation. I can maybe my words is wrong, but it's kind of like to if you have two targets, their noise is overlap. There are some techniques they can separate. This is a very hot topic in acoustic noise localization technology. For this one, it cannot resolve that traffic noise. It will all connected. The sensors will all let the traffic noise go inside.
Yeah, thank you.
Mm-hmm.
Any more questions, suggestions? No.
Okay.
So, thank you, Yongyao, very much for interesting talk.
So,
Okay.
sorry,
Okay.
maybe one more question.
Okay.
So on the slide with the wind with the flow simulation and measurements, so there is this like panel B. So the it's like, am I right that you calculate along the boundary of the microphone? Yes.
Yes. It's this one. You see the figure A. This is the axis. So we measure the pressure field along the y-axis. So because this side is the microphone's membrane side. So this B is actually the distribution of the pressure sensor along this kind of surface, along the y direction.
I mean, yeah, so it seems kind of not smooth. It's
Let
rather
me see.
kind of segment-like.
Yeah, I think probably because of the age of these kind of sensors. If you have the age, and then maybe you can see that probably this part is the age. There's some age effects at these corners.
Okay. Okay.
Yeah. Oh, we can try not to show this kind of the locations out this edge, out the surface of the sensor. Maybe there will be no problem if you only show this region, right? So here, then probably
Okay, I see. So this is just the kind of 0 points. They are beyond the boundary of the microphone. Yeah. Okay.
Yes. This probably the boundary of the microphone.
Okay. Thank you.
Okay. So probably we can put a window here to maybe let people understand that this is the boundary of the sensors.
Yeah, I see. Thank you.
Mikhail?
Yes, also already very technical question. I remember when you have shown that a system with 4 microphones for directional sensitivity.
Right.
Then you had different signal to noise ratio for one direction and for 90-degree direction. But in fact, the system, yes, but in fact, the system is symmetric. The only difference is that one pair is higher up and the other pair is lower down. But in general, I would expect that probably it should be the same, but you see some difference. Is it because of some vertical distribution, or what's the reason for this?
Here, because why we make this kind of array, this one is 3D array, right? It's like a crossed.
Yes.
So the way is because this sensor is not only for this kind of XY plane direction. So because this is 3-dimensional sensor, So you have vertical difference, then it also have the capability to do the vertical detection. For example, here, so you have a sensor here. So this one is XY direction, right? So this is this plan. However, you have vertical directions. It also have capability to do that. But however, it's very challenging for us to do the vertical dimensions. So we only test it for this XY plan. But it has capability for vertical, because our application is actually to locate the targets in all dimensions. Yeah, we can explain that. Yes, this sensor arrays actually can be for whole space 3-dimensional.
Yeah, but so it means that at the moment, pair 1 and 2, they are slightly different from 3 and 4, right? They are different resonators.
Yes. The resonators, you mean whether they are consistent?
Yeah, what you have, yes, what you have labeled 1, 2, 3, and 4,
here?
And now they are different. Is it right?
You mean this one?
No. Back in this, yes, in this one, yes, in this system.
Okay.
1, 2, 3, and 4. Are they all identical, or they have some different?
Yes, they are identical. They are exactly the same by using 3D printings. We tested their response, the consistency of their response. They are kind of a very uniform response for these 4 sensors.
All right. So then yes, I do not understand why there is such a difference, like when you propagate in the direction of 3 to 4 and 1 and 2. Like in both cases, you have 2 along the line and 2 perpendicular, but you see some remarkable difference for 90 degrees and
maybe
or 0 degrees. And I was thinking that's probably because they are at a different level, and maybe your signal propagates like vertically non-uniform, so maybe it's just stronger.
Yes. It must have some difference to make their time of arrival have some difference. Then you can know the direction. So let me
okay,
see.
so they are not exactly perpendicular, so they
So this,
more
you can know this one. Yeah. This is the configuration.
Yeah.
Okay.
Yeah. Okay.
Yeah. So my concern is this work is basically more technical work. It's not the fundamental thing. Maybe a little bit weak. So this is my worry about the issue of this work. No,
well, but practically that's important and a lot of data. So.
But in terms of some fundamental theory, fundamental science, this one maybe not that significant, this work. So this is my concern.
Yeah.
So what do you think about?
We can add some gradients, like you already had a vertical stacked system. You can also try some gradient along, maybe even smooth gradient of the structure, like within one cylinder.
You mean the effective medium model?
Well, in the effective medium model for sure, but probably you can even fabricate the structure such that it inside along the vertical axis, it gradually change structural parameters from top to bottom.
Okay.
Not like step by step in separate stacks, but some continuous variation. Of course, well, it's not clear. Maybe the effect would be just broadening and then it would spoil the story, but at least it's worth trying.
Okay, yeah.
And also try the directional variation as well. Probably that would be fruitful.
Okay, yeah. Okay. Yeah, thank you for the suggestion.
All right, well, that's good.
Okay, yeah. Thank you very much.
Yeah, if there is no any questions, so thank you, Yongyao.
Okay.
It was a great pleasure, yeah.
Okay, see you guys.
So, see you, Yongyao. Bye.
Bye.